The first one in this slot is David Lloyd from EXA Infrastructure, and we will actually keep on a similar topic, namely submarine cables and what else they can do and how they can aid in earthquake detection.
Well done. Thank you. So I'm David Lloyd. I'm a senior engineer at EXA Infrastructure. So I'm going to talk about how subsea internet cables could help detect earthquakes. They're not only good for detecting earthquakes and for tsunami early warning, but they're also good for climate change research, for geology, for protection of cables and security of submarine cables. So very quickly, and for reference, this is the EXA network. So I'll start by covering seismic stations, and then I'm going to introduce 4 methods of detecting or sensing on fibre optic submarine cables. Then I'll quickly compare the 4 of them. So there are many seismic stations around the world today. And looking at this map, you would think there's a lot at sea as well. The problem is most of them are on land. Even those that appear to be at sea, quite a number of those are actually on islands. This is not a great situation when over 70% of our planet is covered in water. There are some sensors deployed at sea, such as the DART buoy system, and they are really good when they work, but the problem is they're not that reliable. At any one time you could have up to 30% or around 30% of them out of order. The red dots in the map here. They can also have difficulty communicating back to land. So wouldn't it be great if we could use existing submarine cables as sensors? Today there's nearly 1.4 million kilometres of submarine cables already installed around the globe. So I'm going to introduce the 4 methods. The first one is interferometry. It's based on phase. The second one is distributed acoustic sensing, or DAS. The third one is state of polarization, or SOP, and then smart cables. So the first one, interferometry. Interferometry has been deployed on the EXA South submarine cable for a number of years now in collaboration with the National Physics Laboratory in the UK and Google. Originally, the entire cable was one large sensor, but later we were able to turn each span between repeaters into an individual sensor, creating an array of sensors right across the Atlantic. And this was made possible through a maintenance loop that's incorporated into every repeater. It's also called a high-loss loopback. And this would be typical of existing repeater submarine cable systems. They'd almost all have it today. So how does interferometry work? This is a very quick overview. An optical pulse is sent into the fibre, and it's looped back on that loop. When it gets back to the receiver, it's compared to what was transmitted, and there will be a phase change. With all things being equal, if there's nothing happening on the cable, like no earthquakes, that will always be constant. However, if there is any disturbance on the cable, that will alter the phase on top of the existing alteration, and that's received at the sensor. And that's actually the principle of interferometry. And it does indeed detect earthquakes. There's an animation coming up here. Just wait for it. So in November 2021, we picked up a 7.5 magnitude earthquake from Peru, and we could see it rippling right across the Atlantic. Similarly, in February 23, it picked up that 7.8 magnitude earthquake from Turkey. We could see it rippling again, the shock waves right across the Atlantic. And we could very clearly see the 2 main shock waves. So the second method is distributed acoustic sensing, or DAS. A device called an interrogator will pump optical pulses into a fibre optic cable. Some of that light will be reflected due to impurities within the fibre, and this is known as Rayleigh backscatter. The interrogator is able to pick up these light pulses, even though they're very minute. DAS is good up to the first repeater, and in some cases a little bit past the first repeater, or about 120 kilometers. So how it works, if everything is normal, the reflected power is going to be, or optical power is going to be inversely proportional to distance. And if everything is equal on the cable, that would be quite linear, similar to an OTDR trace. However, if there's any vibrations on the cable, the fibre will be slightly stretched. They're only minute stretches, but this can be picked up by the interrogator, and it causes fluctuations in the intensity of the reflected power, the optical power. The third method is state of polarization. When light passes through a fibre, it will be polarized, and telecoms operators have known about this for many years, and they've had to compensate for it. So all modern transponders are well able to compensate. If there's any stress to the fibre, the state of polarization will change. The way it's kind of quantified is in a three-state model, or state of polarization model, using Stokes parameters. You can see the small kind of figure on the right-hand side there. So this slide kind of shows very briefly how it works. On the left, you have a figure which shows for a known input state of polarization, there'll be a known output state of polarization. And again, if everything else is equal, no earthquakes, that will be constant. However, if there is any disturbances like figure B, like an earthquake or any major vibrations, the state of polarization will get pretty messed up. And at the receiver, you can see that the output state of polarization is much different than what would be expected, as shown in figure A. And this difference can be interpreted as a valid signal, and it's really the principle of state of polarization sensing. It has been trialled a good few times, and one of the most notable ones was on Google's Curie cable in conjunction with Infinera. And during the trial, they picked up all of these different seismic events and earthquakes. The fourth method is smart cables. In smart cables, there's sensors actually built into the repeaters, the subsea repeaters. You'll have a temperature sensor, a pressure sensor, and seismic acceleration sensors. And smart cables, they're the best at sensing, and you could say they're the gold standard in sensing, really. One of the first smart cables that will be commercial is going to be Portugal's Smart Atlantic CAM cable. And it's going to be ready for service in 2025 or late 2025. It's going to have 50 smart repeaters, and it's going to be funded by the Portuguese government. It'll link up Lisbon, Azores and Madeira. And you notice that the Azores is quite close to three tectonic plates where they meet. Portugal has been interested in earthquakes and tsunamis for historical reasons for many years. Smart cables are the best at sensing, but they're quite expensive. They could be in the order of 20 to 30% more expensive than a standard cable, and they can only be installed on new cable systems. They can't be retrofitted to cables that already exist. So quickly comparing the different methods. On resolution, DAS and smart cables have the best resolution. On range, they all have long range except for DAS, but they all do have their own application. DAS being coastal and the others being oceanic. They do all have their own distinguishing features. Interferometry runs on existing cables alongside existing traffic. DAS is very accurate, but it's short range. State of polarization is very good value, but it's slightly less sensitive than the other methods. And smart cables, they're the best at sensing, but they're expensive and they're only good for future cables. The methods could be combined, or data from different cables could be collated together to get better results or to do some kind of triangulation. So how much early warning could be provided? The figure on the left just simply shows how an earthquake can cause a tsunami. And one of the key points here is that the tsunami will travel at different speeds as it approaches the coast. Deep water, it travels very quickly, but it slows down as it reaches the coast. And then converting all this into times, if an earthquake occurs about 50 kilometers from the coast, you've got at least 20 minutes warning. If it's 500 kilometers from the coast, you've got about an hour's warning. Or if it's 1,000 kilometers from the coast, you've got about an hour and a half. So in conclusion, subsea internet cables can indeed help detect earthquakes and a lot more. There are 4 main methods of sensing, and each one has its own advantages or challenges. And the detection methods can be combined, and data could be collated from different cables to get better results. And detecting earthquakes using subsea internet cables can give early warning of tsunami, which could save lives. Thank you.
Thank you. We have been good on time management, so we do have time for questions. May I? I am wondering, how hard is it to differentiate within the data that is collected between something that points to an actual earthquake or tsunami versus other things that might set off sensors? How much effort goes into that?
Yeah. A lot of it is very academic at the moment because it's a new field. And for state of polarization and interferometry, it's usually experts looking at the data. But as that kind of advances, and you can connect that into kind of machine learning and stuff like that, it'll be able to distinguish, you know. With some of the systems like DAS, that can actually tell from the signature of noise that different vessels would make, whether it's a trawler or it's a cargo ship or there's an anchor very close to a cable. So they have different ways to do it, and it is difficult because it all just looks like noise to a human. But machines can actually determine what actually is a signal and what it's from, whether it's an earthquake or not.
Thank you.
Yeah.
Do we have something on venue loss? Okay, then, thanks, David.
Thank you.